So as I said before, yesterday was spent on creating these graphs, but then, after you have this graph, so what? What's the big deal? Well, you can get a lot of information from graphs, but of course that requires us to be able to process, break down, and actually read it. So as you guys can see on the agenda, we can pull out a lot of information from the graph. We can pull out a function's domain and range from a graph. We can pull out intervals of increase and decrease. We can pull out max and mins. We can pull out specific function output values. Where do all of those components exist on a graph? So let's refresh our memories on some definitions. So by definition, the domain is the set of all permissible. Is it IBLE or ABLE? Permissible. I think it's I.
That looks fine.
Permissible input values. Now, the important thing is, if you're not doing a word problem, if we're not talking about temperature and time, month and the sea level, input values are typically just X's, right? And the range is the set of all the corresponding output values. And again, if this is a word problem, a contextual problems, the output values could be anything. It could be height, it could be length, it could be whatever. But if you're just doing a generic equation, output values are usually Y's. So if I have a graph in front of me to figure out the domain and range, I literally just read where are all my X's, where are my Y's. So I'm just going to draw a generic graph. It's not a specific equation. It's just a random function here. So without loss of generality, let's put it in the first quadrant. This is my x-axis, of course. This is my y-axis, of course. And here is my function, right? There's my lovely function. So pretty. So if you are staring at a graph right in front of you, well, and then you want to know the domain and range, by definition, the domain is the set of all x value that this guy takes. So if you have a graph in front of you, hopefully it should be very easy to read what this x value is. Let's just call it A. And hopefully it would be very easy to read what this x value is. Let's call it B. So the domain here would just be this interval. That right there will be the domain. So in this case, the domain would be A, comma, B. Right. I use square brackets because I use, they were solid points. If they were open points, you'd use open parentheses. The range, you would do the same visual inspection, but the range is going to be the y values. So the y values would be here. Now, if this vertical line is A, then this value must be the function output at A, f of A. Likewise, this must be f of B. So if I ask you, hey, here's this picture, what is the range? You just look at this interval here. That right there is the range. Yeah, you guys can't really see that. Let's use this color here.
Pink.
This right here would be the range. Looks pink to me. And in this case, the range would be f of A, comma, f of B. So notice when you write the domain and range, bless you, it's always least to greatest. So for the domain, it's left to right. For the range, it's down and up. So when I am looking at a picture and I have to analyze domain and range, I always ask myself, okay, how far left does the graph go, comma, how far right does the graph go? For range, I ask myself, how low does the graph go, comma, how high does the graph go? So I hope finding domain and range should be a piece of cake, not too crazy, not too much trouble. So on the practice, you're going to be asked to graph various functions. As far as I'm concerned, you guys paid your dues. You did your hand graphing yesterday. So if you want to use a graphing calculator, if you want to use Desmos to do these graphs, feel free. I'm not going to stop you. As a matter of fact, I encourage you. So let's just do one quick example here. Suppose I asked you to find the domain and range of f of x equals the square root of 4 minus x squared via graphing. Right. So again, if we use yesterday's lesson, sure, this is not a linear function. I'd make an xy table, plot it, see what it looks like. But again, just take a graphing calculator, take Desmos, and get the picture. I'm going to pretend that we did all that, whip out a graphing calculator, type it in. You should get something that looks like this. In case you did not know, this will produce a semicircle with radius 2, right? So if you were to take a graphing calculator or Desmos, that's the picture that you would get. Now, finding the domain and range is very simple. You just read left to right and bottom up. So hopefully we can see that here, that the domain, just read it. It starts at -2, goes all the way to 2. The range is the vertical. Now you have to look at where the actual graphs are. So although the graph, if you were to think left and right, starts here and ends here, I don't really care about that. All I care about is how tall and how short it goes. So that right there would be the range, which we can see starts at 0 and goes all the way to 2. Easy peasy, right? So a lot of these problems, again, it shouldn't be a lot of work. You just look at the picture and analyze it. Okay? Sweet. Other characteristics, other information we can pull from graphs, I sort of expect you guys to be able to do, is to find intervals of increase and decrease. Now this is actually a calculus question. Where is the function increasing? Where is the function decreasing? Since we're not in calculus, we're not going to be using high-level math. Instead, we'll use graphs, right? The important idea when you're analyzing intervals of increase and decrease is that we read from left to right. What do I mean by that? Let's just take a really easy example. Let's take a parabola, right? So I'm just going to do a quick parabola here. Let's say it looks something like this. It looks something like this. And I ask you, hey, find the intervals of increase and decrease. I've had students in the past tell me this. Well, Mr. Vo, isn't it true that this part is going up? And yes, it is true. It's going upwards. But notice how when I trace it, I'm going to erase the highlight here. And I erase the whole graph. When I trace it, notice the only way I can make it go up is if I trace leftward. And that's not how we read functions. That's not how we read graphs. So you have to read things from left to right. So I hope everyone can see, reading from left to right, that this portion here is going down. And reading from left to right, this portion here is going up. So not surprisingly, this part here, the yellow, would be my decrease. Yeah. And this part up here, the orange, would be my increase.
Is this a universal rule?
You always read from left to right, yes.
Like, what if other countries read from right to left?
Well, here's the great thing about mathematics. Even if in other countries where their native way of reading text is from right to left, mathematical functions, when you're talking about intervals, you always go from left to right.
Who determined that?
Who determined that? The great math gods of yesteryears.
Hugo.
Yeah. Now, how do I actually write? I mean, okay, visually, I can see this part goes down, this part goes up. What is my actual answer? When you're writing intervals of increase or decrease, you're looking for the x values. So your answer should be the x value. So let's take a look at the yellow. How far did I shade to the left? Infinity, but it's going to the left, so it's negative infinity, comma. How far does the shading stop? I'm talking about the yellow. At 0, right? So for the intervals of decrease, which is the yellow part, hopefully we can see that it goes all the way to the left, negative, comma, and it keeps decreasing until we reach 0. Now, one important fact when it comes to intervals of increase and decrease, intervals of increase and decrease will always be open parentheses. The logic being, at the place where they are changing directions, going from bottom up, technically speaking, they have no direction. They're not increasing nor decreasing. They are momentarily static, which is another calculus concept we'll get to next year. And then in this example, the interval of increase would be from 0 to infinity, right? So this right here is just the yellow portion. This right here is the orange portion. Easy peasy?
Could you go an example of one or a linear graph?
Sure. Find the interval of increase/decrease of, do you have your favorite linear function? Y equals
Y equals 2x plus 1.
2x plus
4.
4. Why not? Can we all visualize what this will look like? So I'm not going to do very accurate. I'm not going to do tick marks and whatnot. I'm just going to do a quick sketch. So I know that my y-intercept is 4 somewhere up here. My slope is positive 2, so it's going to go something like this. So I did a very lazy way of sketching, but I did it for a purpose because this is a rather trivial example. So if I'm looking for the interval of increase or decrease, I have to find all the parts of the graph that are either going up or going down. Now in this particular line, since we read from left to right, do you see how the entire thing is going up?
Yeah.
So the interval of decrease, there is none. The interval of increase is everything. Negative infinity to positive infinity. Okay. So for linear functions, the interval of increase and decrease is sort of trivial because the whole thing is either increasing or the whole thing is either decreasing. Yeah.
And I have a question. So what would we do for the vertical to the horizontal?
The question was, what would we do if you do a completely horizontal or a completely vertical line? Well, my definitions of intervals of increase and decrease were very informal. If you really wanted to know the technical definition of increasing or decreasing, so I don't know. Can you guys see this? Okay. I'm going to put this in a different color. This is sort of an optional definition. Put it in your notes. Don't put it in your notes. It's completely up to you. But the official definition of increasing and decreasing is this. F of x is increasing if and only if f of x sub 2 is greater than or equal to f of x sub 1 when x sub 2 is greater than x sub 1. Translated in normal English, that says, as I move rightwards, when x sub 2 is bigger than x sub 1, that's moving rightwards, the y values get bigger. F of x is decreasing if and only if, and you guys can probably imagine what it is, everything's just flip. F of x sub 2 is less than or equal to f of x sub 1 when x sub 2 is greater than x sub 1. Whenever x sub 2 is greater than x sub 1, when we go rightwards, the function values get less than question.
Are we going to have to write that notation?
No, that's why I wrote in a different color. It's optional. Right. So to answer the question, what if we have a vertical line or a horizontal line? Well, in a vertical line, you only have one x value, right? So I can't say it's increasing or decreasing because I do not have x values that are going to the right. So we simply say it's just one. You can't describe it in terms of increasing or decreasing. It's undefined. Horizontal lines, however, say that again? But they do change x values. So if I have a horizontal line, say y equals 2, so here's x equals 1, x equals 2. So would you agree that x equals 2 is bigger than x equals 1? Mm-hmm. That satisfies that condition. Is it true that the function output here is greater than or equal to this function output here? Greater than or equals to?
Yeah.
This is technically increasing. But let's read the decreasing definition. Decreasing definition. Is it true that this function output is less than or equals to this function output? Yes, it is. It's or equals to. Or equals to.
The x value will be equal to.
Correct. So the x values are different as expected in the definition. So we have x sub 2 is greater than x sub 1, which is true. Then we have to do this check here. Is it true that the function output at x sub 2 is less than or equals to the function output at x sub 1? Is it true?
Yeah.
Yes, it's true. Yes. Y is certainly this y value is certainly less than or equals to, I'm emphasizing for a reason, this y value. So by this definition, this function is decreasing as well.
So increasing and decreasing.
A horizontal function, strictly by the definition, is both increasing and decreasing at the same time.
So what if it was, what was vertical?
Undefined. However, that's why most mathematicians do not talk about increasing and decreasing. They talk about strictly increasing. So the definition for strictly increasing or strictly decreasing, you would take off these or equals to parts. So when you're talking about strictly increasing functions and strictly decreasing function, a horizontal function is neither.
It will be neither undefined.
Neither. It is constant. Yeah. So, but that's well beyond what I'm going to ask you in this section. So that's why I put it in different color. All that spiel was completely optional. Feel free to ignore it and skip over it. Okay, do we? The last thing that we sort of need to be good at when it comes to analyzing graphs is finding local extrema. Local extrema is just the plural form for local extreme values. Those are simply your max and min values. The word local means around this particular area. So what does that really mean? So I'm going to just draw a random function. It doesn't have an equation, just basically draw a squiggle. Right, there you go. Now this is a very obvious question here. Would you agree that the y value here is bigger than the y value here? Yes, right? So when you think of the word maximum, you think of the biggest. However, if you were to look at a localized area, say this localized area, would you agree that this guy here is sort of like king of the mountain? He's bigger than everyone else around it. That's what we mean by local min and local max. The point here that I highlighted certainly is not the biggest in the whole function, but he's the top dog in the area around the function. So that's what we call local min and local max. So this right here is a local maximum. And of course down here would be a local minimum. How do we find these local mins or local max? That requires a little bit of calculus. Question.
Okay, so when you find that the absolute max, if that max was not filled in, would the local max be the maximum?
So the question was, let's say that this right here was an open circle, and I wanted to find the absolute maximum. Would the absolute maximum be the local maximum? The answer would be no. If this was the picture here with open circles at the end, it does not have an absolute maximum. If this was closed in, he would have an absolute maximum.
If it was ever going.
If it was going forever, he would not have an absolute maximum.
Oh,
because it goes on forever. Right. I'm not.
Wouldn't the absolute maximum be possible?
Well, see, here's the thing. You get some arguments. This is like a debate in mathematics. Infinity is not a number, so I really can't say the maximum is infinity because it's not like 2. It's not like 5. Yeah. We got to get some terminologies down a little bit. I would say, so let's just say this guy here is at x equals a. This guy here is at x equals b. If I'm asking you for the maximum or minimum values, I'm looking for the y values. So this vertical length here is f of a. I would say the local max value, that's the key word there, is the y values, f of a. if I just say, hey, what's the local, like the local max? I don't use the word value. I'm looking for the x value. So I would say the local max occurs at x equals a. Right. And same thing with minimum. Local min value is the actual function output, which is the function output at b in this example. And then the local max happens or occurs at x equals b. Right? And trust me, it happens every single year. I put a problem like this on the tests. Now this is a 5 and this is a 2. And I say, hey, what's the local maximum value? Kids always give me 2, which is wrong. The local maximum value would be 5. The local max happens at x equals 2. That's correct. But the local maximum value would be 5.
So if you don't like specify local max value, it will be
the x value. If I use the word value, I want the y value. Okay. So the key phrase there is value. Okie dokie. Now again, to actually find it, if I don't give you a graph, so if I expect you to graph on your own and find the local max and mins, that is a calculus thing. You will do it next year in Calc 1. So how do I expect you to do it here now in pre-calculus? Well, we'll use technologies. Your graphing calculators can find local mins and max. Desmos can find local mins and max. Since the majority of us do not have graphing calculators, if you do have a graphing calculator, I'll show you one-on-one after class. Most of us will probably use Desmos. So let's just do a quick example here. Find the local extrema of f of x equals x cubed minus 8x plus 1. Right? That's a cubic function. We could technically graph it by hand, but yeah, we have technology for it. Plus, I want to find the local max. It's not extrema. Right? Plus, we want to find local max and mins. We need technology for that. So I'll whip up my graphing calculator, or for most of us, I'll go to Desmos. And then in Desmos, I'll just go ahead and graph my picture. In Desmos, you can do the y equals, you can do f of x equals, or you can drop it completely. So our function was x cubed minus 8x plus 1. Since we don't obviously have Desmos out, I would just watch what I'm doing from here and then just replicate it on your own. So when you graph your function, you'll see your graph here. And well, let me do this so I can actually mark on it. Hopefully we can see that.
Is the vertex? When you do negative b over 2a, is it the x value?
Right here and right here, that's where the extrema are. So to find it in Desmos, it's as simple as just clicking on it. So in Desmos, when you click on the graph, it will actually tell you what the point is. So I'll just take my mouse cursor and just click on where I think the maximum is. There you go. I'll click on where the minimum is. There you go, and boom, there's your local extrema. Easy peasy. So let me just include it into the notes.
So it would be the y values?
It would be the y values, yeah. So if you go on Desmos and you click on the extrema, the numbers will pop up. So I would say the local max value is about 9.709. The local min value is negative 7.709. If I ask you where is the local maximum, the local max is at x equals negative 1.633, and the local min is at x equals 1.633. So finding extrema should be very, very simple. It's just reading the graph. If they don't give you the graph and you have to graph it on your own, just use your graphing calculator or use Desmos to find the extrema. Okay? That's it. That's all I'm going to expect you to do when it comes to analyzing graphs. Domain and range, increase and decrease, extrema, reading function outputs, yada, yada, yada. That is 2-3.